In this video, we'll look at the construction of the NaV-1 Synth project. For complete instructions, visit notesandvolts.com by clicking the link below. First, let's look at the components on the main board. This section is the power supply. It takes a 9-volt input and regulates it down to a steady 5 volts. Next, we have the heart of the project, a Soundgin SSG01 sound processor chip. This section is an audio amplifier based on an LM386 low voltage audio amplifier chip. Next, we have the MIDI input circuit. This 6N138 optocoupler chip is used for protection. Now we get to the brains of the circuit. This is an Atmega 328P microcontroller chip, the same chip that's found in Arduino boards. Finally, we have a 24LC256 EEPROM chip. This is a 256K memory chip that we'll use to store our synth patches. Now let's look at the external components. We have a 20x4 LCD display, a push button, a rotary encoder that is also a push button, a 1/4-inch mono jack for audio output, a DC adapter input jack, and a MIDI input jack. One of my goals for this project was to have it be accessible to as many people as possible. So instead of using a custom printed circuit board that you'd have to buy or have manufactured, I decided to use something called StripBoard. If you've never used it before, StripBoard, or Veroboard as it's called in the UK, is a great way to make permanent versions of your prototype circuits. The top side of the board is just bare printed circuit board material. The bottom side of the board is covered with strips of copper that run from one edge of the board to the other. These strips connect components horizontally across the board. We use jumper wires to connect parts vertically. The board I'm using for this project has 38 holes up and down and 62 holes across. If you follow the link below, you'll be able to download this diagram of the StripBoard circuit. This will be your main reference. This diagram is showing the board from a top-down view like this. The only difference is, in the diagram we can see through the components and the board to the copper strips below. This allows us to easily see all the connections, even the ones hidden by other components. More importantly, it allows us to see where the traces need to be cut. Let's talk about that now. These red symbols on the diagram indicate where the copper traces on the bottom of the board need to be cut. You can easily cut the traces by hand using a drill bit. I use a 7/64 drill bit, but a 1/8 inch would also work. I made this tool by taking the chuck from an old motorized screwdriver and putting it into a small screwdriver handle. To cut a trace, simply take the drill bit, place it into the hole where you want the trace to be cut, and give it a few turns. Definitely don't use a power drill for this, as you'd go right through the board. Just go deep enough to remove the copper layer. If you look closely, you can see that the strip has been cut all the way through. Next, use your multimeter on continuity mode to check that the trace has been cut. You shouldn't hear a beep when you touch the probes across the hole. Now we can begin the actual board construction. StripBoard construction isn't very difficult, but you have to be very careful that you place the components in the exact right location. A part being off by even one hole can ruin your entire board, so make sure you double and triple check your part placement before you solder. I find it useful to have a printed copy of the board layout diagram in front of me as I build. You'll also need a copy of the schematic diagram so you can check component values and polarities. Okay, enough talk, let's start building. We're going to start in this corner of the board. Take a permanent marker and mark the holes located here, here, and here on the top side of the board. Now let's install our first component, this 220 microfarad capacitor. Locate the capacitor on the schematic. This is an electrolytic capacitor, so it has a positive and a negative side. You have to make sure it goes in the correct way. On the diagram, the negative side of the capacitor is shown with this dark band. Here's a photo of the part in place. On the real component, the negative side is indicated by this white stripe. Place the component in the correct location, flip the board over, and solder it in place. Next, grab your drill and cut the traces at these indicated locations. Now let's move to the next component, this resistor. Resistors are colored blue on the diagram. Since this part has no room for a label, we're going to have to check the schematic for its value. As you can see here, its value is 10 ohms. Here's a photo of the resistor in place. It's mounted vertically to fit the tight spacing. Resistors have no polarity, so they can be mounted either way. Next, we'll install this 100 nanofarad ceramic capacitor. These types of capacitors are shown in yellow on the diagram. Ceramic capacitors have no polarity, so you can install them either way. Here it is installed on the board. Now let's install our first jumper wire. I'm using 22 gauge solid core wire for this project. You may notice I'm using 3 different wire colors: green for ground, red for plus 5 volts, and blue for signals. Color coding the wire really helps you catch mistakes while you're building. If you ever see a green wire and a red wire on the same trace, you know something's wrong. To install the jumper, simply take a piece of green wire cut to the correct length, strip the ends, and solder it in place. Try to keep your jumper wires straight and neat. Hopefully by now you're starting to get the feel for this type of construction. Keep going by cutting these 2 traces, installing this electrolytic capacitor, and this red jumper wire. Notice that as I'm installing, I'm moving from one component to the component nearest to it. Use the component you just installed as a reference point. You should find the next component is only 2 or 3 holes away. It's a lot easier to make a mistake when you're trying to count large jumps across the board. Now let's install our first integrated circuit, or microchip. This is an LM386 audio amplifier. Notice that I'm using chip sockets for all the chips in this project. Chip sockets make it a lot easier to replace the chips if something goes wrong, and prevents them from being damaged from excess heat from the soldering iron. As you can see, this is an 8-pin chip. The main thing you have to figure out is which pin is pin 1. All chips will have a mark on one edge. You can see the mark on this chip here. Pin 1 is always located directly to the left of this mark. The rest of the pins are then numbered counterclockwise around the chip. As you install the chips, pay close attention to the location of the pin 1 mark. Installing a chip backwards will most likely damage it. To install the LM386 chip, first install the empty socket as shown on the diagram. Solder it to the board and make sure you cut the traces as shown. I usually wait until all the components are soldered before I insert the chips into the sockets. Now let's talk about the ISP header located here. ISP stands for In-System Programming. Using this connection, we can update the software in our microcontroller without removing anything from the circuit. Looking back at our diagram, we can see that the ISP header has 6 pins. This will fit the standard 6-pin plug found on most AVR programmers. On the board, I'm using a standard 0.1 inch 2x3 male header. If you look closely, you'll notice that the traces between the pins of the header need to be cut. To do this, take a sharp X-Acto knife and begin cutting the copper between the 2 rows of pins. After some time, you'll see a line start to form in the copper. I'm using a pin file to widen this line a little more. Once again, use the continuity function of your multimeter to ensure that the traces are truly cut. Now solder the header in place. A quick note about soldering. Notice how I'm using the soldering iron to heat one side of the pin and then feeding the solder from the opposite side. I'm heating the pin enough so the solder flows freely. Also, try to make sure the soldering iron is only touching one trace at any time. That way the solder won't bridge between traces. Give the joint one last check with your multimeter. One more note about the ISP header. You need to be sure that when you attach your programmer, the cable is inserted in the correct way. If you look closely at your programmer's cable, you'll notice it has a notch on one side. When plugged in, the notch will face this side of the header. I drew this dot with a permanent marker to help me remember. In this section, we'll talk about some additional details you should watch out for. This project contains 2 diodes located here and here on the board. Diodes have a positive and negative side and need to be inserted the correct way. The line painted on the diode indicates the negative side. On the schematic, the diodes are found here and here. On a schematic, this line represents the negative side of the diode. Start with this diode and install it as shown. You can easily see the negative side mark. Here it is on the board. The second diode is a little more difficult to see on the diagram. If you look back at the schematic, you can see the negative side of this diode is connected to pin 2 on the chip and the positive side to pin 3. Here it is on the board. You'll notice we had to mount it vertically because of the tight spacing. If you look closely, you'll see the dark band showing the negative side of this diode. Just make sure that this side is connected to pin 2 on the chip. Now let's talk about the 7805 5-volt regulator located here. Its job is to take the 9 volts coming in from your power adapter and convert it down to a steady 5 volts that the rest of the circuit needs. This component has 3 pins and must be inserted the correct way. This line shows the location of the metal tab that's on the back of the device. And here it is installed. Just make sure the metal tab's in the right location. You also want to keep this tab from touching other components as it will get hot during use. Now we'll look at the crystal oscillator circuits located here and here. These provide a steady clock source to the Atmega microcontroller and the Soundgin chip. The crystal oscillator is made up of 3 components, a crystal and 2 capacitors. These parts have no polarity and can be installed in either direction. The metal case of the crystal can conduct electricity, so make sure that no components are actually touching it. Finally, let's talk about the 2 potentiometers located here and here. Potentiometers come in many shapes and sizes, so the ones you buy may not look exactly like mine. But no matter which one you get, they'll all have the same 3 pins in common. Your potentiometer will have 2 outside pins that will be connected to ground and plus 5 volts. The middle pin is called the wiper. This is the pin that changes when you rotate the control. As long as the pins on your potentiometer match the ones on the diagram, it will be fine. Here are the potentiometers on the actual board. This one controls the output volume, and this one controls the contrast of the LCD display. By this point, you should have all the onboard parts and wiring soldered in place. The rest of the components will be mounted externally. We'll start by connecting the input jack for the 9-volt power adapter. The positive 9-volt wire from your jack will attach to this pad, and the ground wire will attach here. Here's the jack connected to the board. I'm using a standard 2.1mm power jack for my adapter. You can use any type of jack you like, just make sure you run the power and ground wires to the correct spots on the board. I'm using 22 gauge stranded wire for these connections. You'll find the stranded wire is a lot more flexible and makes it easier to position the connectors later. Check the label on your power supply. It should have a symbol like this that tells you how its plug is wired. Next, we'll attach the MIDI jack. As you can see from the diagram, we need to attach pin 4 and pin 5 of the MIDI jack to the board at these locations. You need to be sure that you correctly identify pins 4 and 5 on your jack. If we look at the front face of the jack, the pins would be numbered in this way. But remember, we're only interested in pins 4 and 5. When you flip the jack over, make sure you don't get confused as the numbers will be reversed. Just make sure you identify pins 4 and 5 and solder them to the board. The pins on the back of your jack may look a little different, so take some time and make sure you get the numbering correct. Now let's install the audio output jack. The audio jack uses 2 wires to connect to the board. One wire carrying the audio signal and the other wire is ground. I'm using a 1/4-inch mono phone jack for my board. This will allow me to use standard guitar cables. If we look at a 1/4-inch mono phone plug, you'll see it has 2 parts, the tip and the sleeve. The tip of the plug will carry the audio signals while the sleeve is connected to ground. To attach the jack to the board, simply solder a wire to the tip terminal on the jack and then solder the other end to the audio out pad on the board. Solder a second wire to the jack's sleeve terminal and run that to the ground pad on the board. It's important that you identify the tip and ring terminals on your jack correctly. Here's a trick to help with that. Plug your jack onto a patch cord. Now turn your multimeter into continuity mode and touch one probe onto the sleeve of the end of the cable. When you hear the beep, you've found the correct terminal on the jack. Now do the same on the tip of the cord. In this section, we'll attach the LCD display, the rotary encoder, and the push button. I'm using these 0.1 inch locking headers to connect these components. First, we'll mount the LCD display. The LCD display uses two 6-pin headers as shown here. Solder the male headers to the board as shown on the diagram. Here they are in place. Notice the position of the locking tab. I also marked one of the headers with a permanent marker. We'll mark one of the cable ends as well so we know which header it plugs into. While we're at it, let's install the headers for the rotary encoder and push button. You'll need a 5-pin header for the rotary encoder and a 2-pin header for the push button. As before, install these in the positions shown on the diagram. Here they are installed. Again, watch the position of the locking tab. The first thing we'll do is get our cable ready for assembly. I'm using 28 gauge ribbon cable for the LCD and the rotary encoder connections. We'll start by making the 5-pin cable for the rotary encoder. Take a pair of scissors and cut an 8-inch piece of cable. You'll find that ribbon cable usually comes in 10-wire or 14-wire widths, but we can easily trim it down to what we need. Count 5 wires and make a cut with a sharp X-Acto knife. You'll find you can easily peel the cable. And here's our 5-wire piece of cable. Now take your X-Acto knife and separate the ends of the cable about 1 inch long. Now take a wire stripper and strip about 1/8 of an inch off each wire. And here's the result. Now do this to the other end of the cable. Now we'll attach the plug to the cable. The cable end of the header will come in a kit like this with the female plugs and some crimp-on pins. Here's the 5-pin plug for the rotary encoder with its 5 crimp pins. If you look closely at one of the crimp pins, you'll notice that there's 2 tabs. The front tab grips the bare wire, and the rear tab grips the insulation of the wire, giving the joint a little more strength. To attach a wire to the pin, take a crimping tool that has a 28 gauge crimp socket. carefully place the pin into the crimping tool with the pins facing downwards. And give it a little pressure, just squeeze it enough so it sticks in the socket. Grab the ribbon cable we prepared earlier. Now take your crimping tool with the pin in place and insert the wire through the back of the pin just far enough that the insulation is making contact with the rear tab of the crimp pin. Now squeeze the crimper firmly. If all went well, you should find you have a good solid joint. Because of the small diameter of these wires, you may find the front crimp tab isn't gripping the wire quite strong enough to make a good connection. In that case, take your crimping tool and find a flat spot like this that closes down to nothing. Insert the crimp pin into this spot and squeeze it down until it makes good solid contact. Check each pin you do with your multimeter on continuity mode to make sure it has a good connection. And here's the finished cable with all the pins attached. Now take your multimeter on continuity mode and give each wire one final test. Now we'll look at the soldering process. First, add some solder to the pin of the rotary encoder and also the bare end of the wire. Now cut a piece of heat shrink tubing and place it over the wire. Now hold the wire against the pin of the encoder. Apply heat with a soldering iron until the solder flows and makes a connection. Make sure you have a good joint. Once you've soldered all the joints, slide the heat shrink tubing over the pins of the rotary encoder and use a lighter to shrink it tight. Make sure you don't use too much heat as you could damage the component. The final step is to insert the pins into the connector. On this connector, the pins are shaped in a way that they'll only fit in one direction. Simply loosely place the pins into the slots. Once all the pins are in position, take a small screwdriver and carefully press them in until they lock. Once you've made sure all the pins are fully inserted, you're done. Let's talk a bit about the rotary encoder. I'm using a panel mount version with a built-in push button. If you look at the back of the encoder, you'll see it has 5 pins. These 3 pins are connected to the encoder, and this group of 2 pins is for the push button. Rotary encoders require 3 pins for connection. The 2 outside pins are data pins, and the middle pin is used for ground. If we look back at the diagram, the rotary encoder's 2 data pins will connect here, and the ground pin will connect here. The 2 data pins of the encoder need to be connected in the correct order. If you look at the back of the encoder from this orientation, the pin on the left will go to the top pin on the board. The pin on the right will connect here. If everything goes to the right when you turn the encoder to the left, you'll know that these 2 pins are in the wrong order. Now connect the rotary encoder's middle pin to the ground pin on the board. Finally, we'll connect the 2 push button pins to these 2 locations on the board. For push buttons, the order doesn't make a difference. Now we'll install the second standalone push button switch. It connects to the board using this 2-pin header. This cable is built in the same way as the rotary encoder cable. I used 22 gauge stranded wire for this cable since there's only 2 connections. Since this is a push button, the order of the cables doesn't matter. They can go either way. The last component we need to connect is the LCD display. The display I'm using is a 20 character by 4 line HD 44780 compatible model. These types of displays are all interfaced using these 16-pin connectors. If we look at the back of the display, we can see on this model the pins have all been conveniently labeled for us. If that's not the case on your display, you may have to look at the data sheet to verify the pins. If you notice, in our project, we're only using 12 of the 16 pins. To connect the display to the board, you're going to need to create 2 6-pin header cables the same way we did with the rotary encoder. If we look back at the diagram, you can see the 2 headers on the board are labeled. When you're wiring the cables, you just have to double check that each pin on the board is wired to its matching pin on the display. You can see how the labels on the diagram and the LCD display mostly match up, but there may be a couple of differences depending on your board's manufacturer. On my board, the pin I've labeled as cont or contrast is VO on the actual display board. VCC on my board is VDD on the display, and ground is VSS. Once you've built the cables and soldered them to the display, you have completed construction on the board. Before you power up the board for the first time, it's good to go back and do some final tests. I do this before I plug in any microchips. It's best to find any mistakes before you damage expensive components. First, do a thorough visual inspection of the board. Refer back to the schematic and StripBoard diagram and check that all the connections are going where they need to go. Also, make sure you haven't missed any cut traces. Now, take your multimeter and set it to continuity mode. Touch one probe to any green wire. Now, take the other probe and touch it to all the other green wires on the board. You should hear a beep each time, as they should all be connected. Also, touch the probe to any pin on a socket that is supposed to be grounded. Use the schematic to identify these pins. Once you've done this, do the same thing with the red wires. This will check the positive voltage leads. Now we're ready to apply power for the first time. Plug your 9-volt adapter into the board. Set your multimeter to measure DC volts. Attach the negative probe to any ground location on the board. Now take the positive probe and measure any pin on a chip socket that should be getting 5 volts. Once again, check the schematic for the location of these pins. You should be reading roughly 5 volts on your meter when you do this. Don't forget to do this on the header pins as well. If everything looks good, disconnect the power from the board and insert the microchips. Remember to double check that you put them in the correct way. Now we need to program the microcontroller using the ISP header. I'm using an inexpensive AVR Pocket Programmer from SparkFun. It's cheap and it does the job. But any other AVR programmer you have should work equally well. The Pocket Programmer has an option to power the target from the USB port. We're not going to use this as we'll be powering our board by its own power supply, so turn the setting to no power. If you're using a different programmer, it may or may not have this option. Connect the programmer to your computer using the USB cable. Now take the programmer's 6-pin cable and attach it to the ISP header on the board. Remember to locate the notch on the cable and make sure it faces this side of the header. Now connect it to the board. Finally, we'll power the board by attaching the 9-volt adapter. First, download the latest software from the notesandvolts.com site by clicking the link below. Open the folder and locate the NaV-1 Eno file. Open this with the Arduino IDE. You'll notice that the other files in the folder will open as tabs. Now go to Tools, Programmer, and verify that your programmer type is selected in the menu. Now go to the Upload button. Press the Shift key and this will change the option to upload using programmer. Once that is set, click the button. You can see the progress at the bottom of the window. This will take a few minutes to complete. Once completed, you should see Done Uploading and no error messages in this space. Now plug in the LCD display, Rotary Encoder, and push button. Now keep an eye on the display and apply power. It should immediately light up and display the Notes and Volts title screen. Adjust the contrast potentiometer on the board until you can see the text clearly. Now we can test the other controls. The patch number should increase as you turn the encoder to the right and decrease as you turn it to the left. Now press the encoder button to change the cursor. Move to the Edit menu and press the button again. Press the standalone push button twice to exit this menu. If everything went as described, congratulations, your controls are fully functional. The EEPROM memory chip needs to be formatted before first use. To do this, unplug the power to the board. Hold down both the Rotary Encoder button and push button, and then apply power to the board. You have to keep these two buttons held during the entire boot up sequence. On the display, after the initial title screen, you'll see it go into its initializing EEPROM sequence. You only have to do this the first time you use the chip. The memory is now formatted and ready to use. Now for the final test. Power up the board. Connect the audio out to a line level amplifier or mixer. And connect the MIDI input to a MIDI keyboard or sequencer. Set the keyboard's MIDI out channel to Omni and try to play some notes. Finally, adjust the board's volume potentiometer to give a strong but not distorted signal. Congratulations, you've completed the project. Check back at notesandbolts.com for software updates and other projects. Once again, thanks for watching.